3.2, nonlinear models. There aren't many in this section. This whole thing's about 10 pages. We only have methods to solve linear first-order differential equations at the moment. The integrating factor method can only be applied to, we know how to solve some other things. The integrating factor method only applies to linear first-order differential equations. If the differential equation is nonlinear, our only hope is that it's separable or exact, right? And all of the problems that we're going to see are separable equations. Here's the first kind, population dynamics revisited. If PT is the size of a population at time t, the model for exponential growth assumes that dp dt is kp, right? However, what if dp dt was equal to the population times some function of the population, right? So instead of a constant, it's a function of the current population, right? The rate of growth of the population is proportional to the population, or is equal to, the population and some function of the population. So now instead of k, we have this f of p. This is the so-called density-dependent hypothesis of population dynamics. And let's recall that these are the so-called autonomous differential equations, right? The right-hand side only has p's in it, right? No t's. We analyzed these using the Fortress and Page portraits diagrams in an earlier section. The short recap is that when you have values of p for which f of p times fp equals 0 are the critical values, and all the interesting stuff happens in between the critical values. Here's an example. Logistic population growth. Exponential population models are okay. They do a pretty good job, but they imply that growth is unbounded when in reality we live in a finite world, right? There's only so much land, so much resources. If we let k be the maximum population a system can support, then the logistic population model is this, where r is some constant, and k is the maximum population of the system, right? This is what's called the logistic model of population growth, right? The logistic model of population growth. And in general, you can solve this, right? This is only in terms of p's, so you can divide it across. This is in terms of t, so you can push that across. And it's a separable equation. If we have, so in general, we just write this equals a, this equals b, right? But in reality, there's some rate and some constant and some cap. So if we have p equals a minus b times p, then separation of variables gives this, and splitting this along the multiplication is partial fractions again. Partial fractions. Which means, you can figure this out if you do the partial fractions, right? If you write 1 over p times a minus bp equals some big A over p plus some big B over a minus bp, and you do the partial fractions on that, you'll get 1 over a and b over a. And then integrating both sides, integral over here, right? This becomes 1 over a times natural log p plus, I guess you get a minus sign out of this chain rule, minus b over a natural log of a minus bp. And then over here you get t plus c. And then combining these together, I guess you should multiply through by a. Right? This is b squared, 1 over a, multiply through by a, and then what happens to this b squared? A minus bpp. I'm not sure what happened to the b squared. Oh, this should be 1 over b. This should be 1 over b. 1 over b. Because we're integrating, right? We're integrating. 1 over b times b. These cancel. Multiply through by a. A, this becomes a and ac over here. And then we have natural log p minus natural log a minus bp. Subtraction outside of natural log becomes division inside. And then we can raise both sides to the exponential, right? We get p over a minus bp equals some constant e to the at, which means p of t is equal to a constant over b constant plus e to the negative at. And since p of 0 is equal to p naught, then if p of 0 is not a over b, we have p of t equals a p naught plus b p naught plus a minus b p naught e to the negative at. And note that in this case, k, the limit of the population is a over b. Which means we can normalize this a little bit by dividing down here by b, dividing down here by b, dividing up here by b. We get a over b p naught plus a over b minus p naught e to the negative at. And this is now our k, right? Remember that k is the limit of the limiting value of the population. So this is the general solution. Please just memorize. Memorize this. For the logistic model, this is it. Since we're usually giving the limited population in these problems. Okay, here's an example. Suppose a single fish carrying the fish flu is released into an isolated lake containing 2,000 fish. If the spread of the fish flu is governed by the logistic equation, after 3 days, the number of fish with the flu is 60. Determine the number of infected fish after 6 days. Okay. We know the maximum number of fish that could be infected is 2,000. And we know that a single fish was released on day 1. So x naught is 1. Since we know that x of t is equal to k e to the, wait, what is it? K p naught. This is p naught. Right? X of t is equal to k p naught plus p naught, over p naught plus k minus 1 e to the negative at. Right? K minus p naught. E, yeah, okay. This is just copying down that previous thing and plugging in for k. And that means that in general, our number of infected fish at time t is given by this equation. But we don't know what a is. But thankfully we can use our secondary condition that after 3 days there were 60 fish to pin down a, right? So when t equals 3, x equals 60. X equals 60 when t equals 3. And solving this for a means a equals 1.3748. So that means our true value of x, our true function for population dynamics, is 2,000 over 1 plus 19999 plus e to the negative 1.3748t. And after 6 days, there should be about 1,313 infected fish. Okay, this is about it for the nonlinear case, right? There's only one type of problem in the section 3.2. And they're all, it's just population dynamics, right? Okay.